Who are you planning to murder?
No. I'm planning to silence.
That's smart. Don't admit who you're planning to murder on video. That's a very smart. Just speak in vague generalities. Say, "Oh, I'm not planning to murder anybody. Oh, how could I possibly do that?"
He might be my chemistry teacher. I don't know.
Oh, that's smart. That's so good. Be ominous and threatening at the same time.
Give me 100% of my money.
Okay, well now that was an outright threat. So now I can take the video to court, and I can. What will be okay?
You're above the age of 18, so you kind of have to take responsibility.
I take responsibility for you threatening my life? Oh, okay.
I'm not old enough.
That's right, yes.
I'm still a child.
You minors, you get away scot-free for everything. Okay, let's try this out. We are not going to go through the exam, even though your marks are up on Power School. We're going to go through the exam tomorrow. Or Friday, we'll see. You have a quiz on Friday.
Quiz over?
Yeah, it's been up on the calendar all week.
3.1?
What?
About 3.1?
Yeah, kind of. It's going to be about 3.1 and 3.2. Our idea is that we want to get to Lewis structures by the end of kind of the middle tomorrow. Hopefully, actually, by the end of today, we'll talk about Lewis structures. Now we finished what? What? No, those aren't Lewis structures. These are structural models. Yeah. So these are three-dimensional representations of they're typically organic chemicals. I don't know. Hopefully, you can see in these models. There's lots of black atoms. Does anybody know what the black atoms are?
Carbon.
They're carbon. Yeah. So these are organic molecules because they have many carbon-hydrogen bonds in them, and that's kind of the loose definition of what an organic molecule is. No, we want to get kind of close to that. Okay, so we want to start talking about how atoms get put together, and then eventually we want to talk about what shape do they make when we put them together. If I put 3 of these things around one of these things, then what shape is it going to make? Yeah, and I'll give you a hint when we come back from the break. Do you see the models that are dangling from directly above Maya's head, basically? Yeah. So we're going to be talking about those. The angular, or bent, the trigonal planar, trigonal pyramidal, and the tetrahedral. Yeah, sure. Yeah, basically, yeah. And so we'll talk about it later. But we want to just kind of recap what we were doing yesterday. So take out your 3.1 bonding notes if you have not already, please. Hopefully they're in the bin. Oh, somebody knocked down my world model. Do you know who did this?
John.
It was probably wow, snitch. Yeah, way to snitch on me. Not snitch. She's throwing you under the bus.
I didn't know from the forest.
She's a snitch. Idris, was it you? No?
Can't even reach that.
You can't even reach that high. You're taller than I am, and I can reach it.
I remember you grew up in 6th grade.
Yeah, it was me.
Also, you said that Roy was being a snitch.
Okay, it wasn't me. It wasn't me.
I don't know why you would say Roy's being a snitch if he wasn't truthfully speaking about you. Yeah, that's right. So it was Roy. That's what you're saying. So you're snitching on Roy. I don't know. I'm paraphrasing what you're telling me. Okay. A bond is a result of an electrical attraction. Positives are attracted to negatives. Good. So we can glue 2 positives together. Just get off your phone. There's no reason to be on your phone. It's okay. Finish your text to your mom because that's who I'm assuming you're texting right now. There's no other person you would text right now. So positives can be glued together as long as what's in the middle? Negatives. So what that means is electrons are the glue that hold nuclei together. Nuclei are positively charged. So if we want to glue 2 nuclei together, all we need are some electrons to bond them together. Does that kind of make sense? Yes. So we can think of a pair of electrons as the glue that holds these two nuclei together. Perfect. Chemical reactions depend on an atom's valence electrons. We'll talk about that later. And an orbital, that's where we put those electrons in that energy level. Then we started talking about, okay, what does this energy level diagram mean? This is old news, though, right? This is from last year, and we reviewed it at the beginning of this year. When I look at this, what changes when something goes from an atom to an ion? What's the only thing that changes?
The electron.
The valence electrons. Would you agree with that? It's always just the valence electrons that change. So really, chemical reactions are like a study in valence electrons. That's really all chemistry is. Chemistry is the study of valence electrons. Fluorine atoms gain an electron, but they gain in the valence orbital, right? So then we said, okay, rules for these orbitals. First energy level has room for 2, and then 8, and then 8. And I'm curious, do you know how many could fit in the fourth energy level?
16. 18.
So 2, 8, 8, 18, 18, and then after that, I don't know. It's like 32 or something like that. Above the first energy level, there can be 4 orbitals, 2 electrons each for a maximum of 8. And we're not going to get any bigger. We're not going to talk about things in the 4th, 5th, or 6th energy level. That's just ridiculous. Electrons spread out, or they repel each other, and they fill up empty orbitals before pairing up. So that's why when we looked at this diagram, we had to put electrons in this orbital, then that one, then that one, then that one. Then once we half-filled every orbital, then we were forced to put them as being paired up, right? We were forced to do that. So a bonding electron is a single electron all by itself. How many bonding electrons does beryllium have?
1. 0. 4.
A single electron in an orbital that could be shared with another. How many single electrons could be shared when we look at beryllium? 2. Can these 2 electrons be shared if they're not in the valence orbital? No, if they're not in the valence shell, then they can't be shared, right? We've got 2 unpaired electrons, one up here and one over there. They can both be used for bonding if we wanted to. Okay, and then we started talking about Lewis symbols, and this is where we're going to try and really focus a lot of our attention for kind of the next 10 minutes. Lewis symbols are symbols that contain dots which show how atoms bond. A hydrogen atom. How many bonding electrons does hydrogen have? 1. Hydrogen can form 1 bond. That's it. It cannot form more than 1 bond. It's got we say it has a bonding capacity of 1 because it can only form 1 bond. The elemental symbol represents the nucleus and the filled energy levels, right? So when we look at an oxygen atom, this is like the Bohr diagram, right? The symbol O represents all of this junk. Okay, do we care how many protons are in oxygen? No, that doesn't matter for chemical reactions. Do we care how many lower level electrons are in oxygen? No. All we care about is the number of valence electrons. That's it. So when I look at oxygen, how many bonds can oxygen form? 2. It's got 2 like single valence electrons, right? 2 bonding electrons. How many lone pairs of electrons does oxygen have? It's got 2. Remember, we only care about the lone pairs if they're in the valence shell. That's all we care about. So this thing has 2 lone pairs. Its number of lone pairs is 2, and its bonding electrons is 2 as well. So it can form 2 bonds with things. Okay, So an oxygen ion has a charge of -2. So that means it must have what? Gained or lost electrons? Electrons are negatives, so we must have gained negatives, right? You can only gain or lose negatives, right? So we gained 2 negatives, right? Okay. Our Lewis formula looks like this. We're going to amend this a little bit. Does this thing have a charge on it? Does this thing have excess positive or negative charge? Excess negative. It's got too much negative, right? So what we're going to do, we're going to put some square brackets around it, and we're going to say the whole thing contains a 2 negative charge. The entire kit and caboodle contains a 2 negative charge. It's not really anywhere in particular, it's just there. What am I doing here? Can I move on? Is that okay? Yeah, all right. So then we talked about neon, and neon's very stable. Does neon like to react with things? How many bonds can neon form? None, 0, right? I mean, theoretically it could if you really put it into like extreme circumstances, but it doesn't look like it can form any bonds, right? All of its valence shell, its entire valence shell is full. It's got no bonding electrons, all lone pairs, so it doesn't look like anything can happen there. We're going to start talking about electronegativity. I just want to see, no, I just want to see, that. Sure, let's go ahead and do this. Okay, electronegativity is a measure of how strongly electrons are attracted to a certain atom. Okay? Now, what I want to bring your attention to is, do metals like to lose or gain electrons? What if potassium was to turn into an ion, would it become positive or negative? It would become positive, right? So what that means is that potassium, which is a metal, it tends to lose its electrons. Now let's go all the way over to the other side of the periodic table, and let's look at fluorine. Fluorine, does it tend to lose or gain electrons? It tends to gain electrons, right? When it goes from an atom to an ion, it tends to gain electrons. And so this is interesting. Do you think we could measure or quantify an element's ability to lose or gain electrons? Sure. I think we could too. We could at the very least, we could use a relative scale for how badly does this thing want to gain or lose electrons. What? What? They all have the noble gases don't have, the noble gases have blanks. Yes, some of the metals. If I'm being perfectly honest, Wim, I don't really know why. I think maybe it's because their chemistry is just complicated and it's hard to study them, that if I were to take a stab at it. Wim, I'm going to be perfectly honest, that's not something I've ever really thought of. Yeah. Just because I only really care about kind of the main group of elements, and I only really care about a lot of the stuff that we deal with on a daily basis. Whether or not europium has a really high or low electronegativity is not something I've ever asked myself. But that's a great question, and maybe I'll look into it on one of these days. Okay, a number, electronegativity, is a number which describes the ability an atom has to attract a bonding electron from other atoms in its orbitals. The number is found above the element symbol. So for example, hydrogen has an electronegativity of 2.2. Great, awesome, that's fantastic. But what does that mean? Electronegativity is a relative scale, and find for me the lowest electronegativity you could possibly find. Go ahead and find the lowest electronegativity on that periodic table. Hydrogen's pretty low, but it's not as low as some other things.
Potassium.
Oh, yeah.
Franklin.
Helium.
So when I look at it, yeah, hydrogen's pretty low. It's 2.2, but it's not as low as lithium. And lithium's not as low as sodium. And sodium's not as low as potassium. Francium. That's right. Okay? And so francium, basically the lower the electronegativity, the more weakly held the electrons are. This thing doesn't really want those electrons. It'll take them. If it's forced to take them, it'll take them. But it doesn't really want those electrons. Okay? What's the most electronegative thing that you can find? With an electronegativity of 4.0. Fluorine, right? Yeah. So the electronegativity is basically like if this atom was in a tug of war, how hard would it fight for electrons? That's kind of what you want to ask yourself. So let's draw probably the most famous chemical on the entire planet. What's the most famous chemical? What's the first chemical formula you probably ever learned? H2O. Probably H2O. So let's draw H2O, if that's okay with you. I want you to tell me, this is H2O. It's got a hydrogen bonded to an oxygen, which is bonded to another hydrogen. What is the electronegativity of this hydrogen? 2.2. See, the electronegativity is 2.2. What is the electronegativity of the oxygen? Who's going to pull harder on the electrons that they share? Oxygen. So what that means is that this bond, remember a bond is the glue that holds these nuclei together. What is a bond made out of? Electrons. It's made out of 2 electrons. Every bond is made out of 2 electrons. Who's pulling harder on these electrons? Oxygen is pulling harder on the electrons. The electrons spend more time with the oxygen than they do with the hydrogen. That doesn't mean they spend 0 time with the hydrogen. It means they spend less time with the hydrogen. Okay? So that's all that means. That means oxygen is winning the tug of war for the electrons. You know what a tug of war is, right?
Yes.
I think we need a demonstration.
We don't need a demonstration. We know. I'll draw a picture. Perfect. So this is perfect. So here, do you know what I'm trying to draw?
No. That's the finish line for a race.
That's not the finish line for a race. So. Oh my God.
Isn't it a line in the middle?
Yeah, it is a line. Actually,
No, that's a road.
No, they have like a little section in the middle.
There's a little section in the middle is the problem. And so there's a little flag that drops from the rope. And so this team wins over here. They win the tug of war if what happens?
Their flag gets to their side.
If the flag crosses that line, right? That's the idea behind a tug of war. Now, these people are fighting for a flag, but what's happening in a chemical bond? They're fighting for 2 electrons. They are sharing them, right? Remember, they totally are sharing them. I didn't bring it up.
You can do that.
I didn't want to bring it up.
The electronegativity.
You feel what they're feeling.
Okay. I moved classes this summer, so I can't really find what I would typically use for this demonstration because I don't know. There's somewhere in the classroom. It doesn't really matter. Whatever. It's fine. So basically, I have an electron. Okay, I have an electron, and you can catch, right? Good. Fantastic. Okay. So I have an electron. And so that means how many bonds can I form? I can form 1 bond. And I notice Aaliyah also has a spare electron. Okay? Now, I would really, really, really enjoy it if I had more electrons, and so would she. So here, you can hold, but you gotta hold it, and I can hold. And so if I fight really hard for these electrons, and Aaliyah fights really hard for these electrons, is either one of us going to let go? No, we're both bound to the electrons. Yeah, I know you will. We're both bound to the electrons because we're both fighting really hard for them. The harder we both fight, the more we both share the electrons, the stronger the bond will be. Is that kind of okay? A little bit? Yeah. And so what happens if one of us fights really hard? Okay, so I'm going to take this back. What happens if one of us fights really hard? You got to fight really hard for the electrons. And if I fight like a little bit for it, what's going to happen? Here, I'm going to fight a little bit for your electron, and you fight really hard for my electron. Okay, really? So what happened?
That was lit.
Yeah, well, she ended up with both electrons, so I lost an electron. What did I turn into? If I lost an electron, I turned into an ion. I turned into a positive ion, and she turned into a negative ion.
Wait, why would she turn into a...
Oh, yeah, never mind.
It's a negative, right? Can I steal them back from you? Yeah, I won. Oh, there we go. So this is what a chemical bond is. A chemical bond is both of us holding on to the electrons. And if we're both holding on at approximately equal strengths, right? If we're both holding on approximately equal amount, then we're sharing them. Because neither one of us is going to let go. But if one of us is way more powerful than the other one, then what's going to happen? It just rips the electrons away from the other. And they turn into ions. Yeah.
Does oxygens hold like the same for both, or is it split between?
No, oxygen. This is its electronegativity compared to that, and this is also independently its electronegativity compared to that. So it's fighting equally hard for both in both bonds. Okay. So what I want you to do is I would like you to identify the electronegativities. Just go searching for them. It's just like a little scavenger hunt with no prize at the end.
What for?
Gee, I wonder, John.
No, I'll share it with you.
Yeah.
You don't have to thank me.
Oh, yeah, thanks, John.
I need that back.
Oh, it's
W. But why is tungsten W?
Because its proper name is wolfram.
Why is so much cooler?
Yeah, it does. It's the Latin name for it, right? It's like why is iron Fe?
Yeah.
Ferrous and ferric. The
I
Latin
like iron
names.
better.
The Latin names. Why is copper Cu and not Co?
Flat.
Cuprous and cupric.
Cobalt.
Why is mercury? Why is lead Pb?
Peanut butter.
No. Because it was used in aqueducts in early plumbing.
That was a stretch.
We called it no. The Latin name for lead is plumb.
That's right for helium.
Yeah. What? It's because the Latin name for tungsten is wolfram, and we still call it wolfram a lot of the time. Remember, this is tungsten, right? Tungsten is just a metal. It's a metal like any other metal. Right? Aluminum, tungsten, aluminum, tungsten, aluminum, tungsten.
Oh my god.
Yeah, oh my god. What? Oh my god. Okay. Aluminum, tungsten. Right? Or wolfram, I guess we should call it. Right? Aluminum, tungsten.
No, we had a chem teacher who said that. Was it? Do you remember?
Yeah.
Do you remember Mr. Stone?
Yeah.
And how he had like tungsten ring and he'd throw it on the ground because it made a cool sound.
And
And it broke it.
that's because it was tungsten carbide. It was actually a semi-ionic.
He was like, see, it was like, see, and it never breaks. It never breaks. Never broke.
Aluminum and tungsten, right?
I mean, it's glass. That was so
I
funny.
don't know what it was.
That's it wasn't it wasn't metal, right? It's not like I have a metal. Because that's what he was talking about, right? He's saying it's not going to shatter, it would bend, if anything.
Yeah.
Yeah. So I have this is made out of steel, which is an alloy of metals, right? And I could do whatever I want to it, right? But his was tungsten carbide. And his tungsten carbide acts more like an ionic compound. So it's brittle, it's not malleable.
It's too good. It was just like, it was oh, that was funny.
Did we do this last year?
Ron.
How do you say it?
Electromagnetic.
Crazy.
Say, okay, say trigonometry. Trigonometry. Electromagnetivity. Electromagnetivity. Say it. Magnetivity. Electromagnetivity. Say it again. Electromagnetivity. Say it. Magnanimity. Okay, no. Say it.
Electronegativity.
Magnanimity. You realize you're sick. Most electronegative. I'm not stealing. I'm borrowing them and giving them back. Watch out back. I don't need their permission to let me borrow their stuff.
It's interesting.
That's what people should act like.
That's what I have. I believe in that.
No, that's fine.
Yeah.
If you're interested,
I felt like this could be something.
no.
Iron's stealing.
All right, whatever. Okay. Sodium. What's sodium's electronegativity?
0 point.
Which one?
0.9. They had a lot.
What's iron's electronegativity? What's Wolfram's electronegativity?
Wolfram, is that general?
That's the property name for tungsten, but whatever. What's aluminium's? What's francium's? 0.7. Okay, what do you notice about everything in here? They're all under 2, and they're all what classification? They're all metals, right? Okay, what about nitrogen?
3.0.
What about fluorine?
4.0.
What's helium?
Negative.
It's blank. Why?
Because it doesn't want it.
Because it doesn't form bonds. In order for us to measure electronegativity, we have to figure out how hard does it pull on the electrons in a bond. Xenon has electronegativity because it's so big, under some conditions, you can force it to bond with things. And so we can measure its electronegativity. Carbon? Oxygen? Good. Okay, so on the periodic table below, where's the most electronegative thing here?
Second row and 17.
Right? Where's the least electronegative thing here?
7.
What do you notice? What do you notice in general? I'm not saying this happens every time, but in general, as you go from left to right, what do you notice happens for the electronegativities? They're getting bigger, right? So they increase our electronegativities as we go left to right. In general, what happens as we go top to bottom?
One more.
As we go top to bottom?
The other way around.
Yes, start at the top and go to the bottom, it starts to decrease, right? So, hopefully it makes sense that the least electronegative thing will be in the bottom left and the most electronegative thing will be in the top right. Now, the reason why that is, I'm not going to test you on this, but I would like you to listen up. I'm going to draw a picture of fluorine. The picture of fluorine goes like this. It's 9 protons with 2 electrons here and 7 electrons on the outside. So how closely are the valence electrons held to the nucleus? Are they pretty close? I would argue they're pretty close. That's not bad. Let me show you what the valence electrons are like in francium. What energy level are the valence electrons in? Yeah, are they in the first energy level? No, the second, third, fourth, fifth, sixth, seventh? Yes, they're in the 7th energy levels. And so when I look at francium, it's got 87 protons in the middle.
87?
It's got 87 protons in the middle. But let's look at its energy levels. That's the first one. That's the second one. That's the third one. That's the fourth one. That's the fifth one. That's the 6th one. And that's the 7th one. So where are the electrons being held? Out here. How strong of an attraction do you think there is between these protons and this one itty bitty little electron?
Not that strong.
Not much.
It's so difficult. It's so difficult to really have a strong interaction because the distance is so far. So it's like oh shoot, I threw them away. It's like if I were to hold in a tug of war, if you were to hold onto your electrons, what do you think? Would it be easier? Would you have a stronger hold on your electrons if they were right here? Or would you have a stronger hold on your electrons if they were right here? The first one. So the closer the electrons are held, the stronger they can pull on it. But the further the electrons are away, the weaker a hold you have. So it's very easy for something to come by and just steal francium's electron away from it. Does that kind of make sense? Yeah, hopefully that does. Wim.
That was like the lowest electronegativity is like 7, like the maximum amount of rings.
I don't know of anything. There are elements that have just been added to the periodic table in the last 3 years, and they complete the 7th period, but there's nothing in the 8th period. We've never been able to. Theoretically, it might be possible to get something in an 8th energy level, but we've never been able to see it, and it would probably be so unstable it would exist for a trillionth of a second and then go on. Yeah.
So what about why the non-metals so much stronger?
Why are the non-metals? Why do the non-metals?
Like yeah.
Why do they have a higher electronegativity?
Yeah.
Okay, so that's a really good question. So just because you asked, let's look at something, let's compare something that has the same size as fluorine. What's the first element in that row, in the same row as fluorine? Lithium, right? So let's talk about lithium. How many protons does lithium have? It's got 3 protons. And so its 2 energy levels are its first one's filled up and its second one is not quite filled up, okay? Do you think this 1 electron would be more attracted to these 3 protons, or do you think it would be more attracted to these 9 protons?
The one, yeah.
Do you see what I'm saying? It's the same size, right? The size is approximately the same, but because there's more positive charges, the further to the right in that row you go, the stronger attraction there is. Does that make sense? So that's explaining both of these properties of electronegativity. And if you didn't get that, if you're like, man, that was way over my head, whatever, it's all good. Don't worry about it. Don't worry about it. I don't actually want you to do this. I want you to do something else. It's right here. We're going to work on the front side of this sheet. Don't touch the back side of the sheet, please. Just work on the front side.
I wish you can make nuclear bombs for running this. What is valence?
Why is there such a huge space for that?
The outer shell will go one after the first one.
Okay, can we go through the first one together, please? I want to do the first one together, then I'm going to give you, 6 or 7 minutes to finish it, the front side, and then we're going to talk about something else. So sodium, what is sodium's electronegativity?
0.9.
I don't know why this isn't working for me, but
Use a marker.
say use a marker. Use a marker on the smartboard. Okay. Okay, its electronegativity is 0.9. I'm curious, how many valence electrons does sodium have? Do you remember the shortcut?
9.
It only has 1. Why does it only have 1 valence electron? Wim?
Well, because the first two is like 2 and 8 and 10 is 1.
Okay, so that's one way of thinking about it. Shh.
Did you say you had like count on the side?
Yeah, absolutely. You could say how many electrons can fit in the first energy level? 2. 1, 2. Then we're full, right? So helium and then or hydrogen and helium, and we're full. Okay. Then lithium. How many valence electrons does lithium have? It's got 1 valence electron, because we can fit a maximum of 8 in that energy level, right? It's only got 3. So we put the first 2 in the first energy level, and then the third one goes in the first spot of the second energy level. How many does beryllium have? 2. It's over twice, right? How many does aluminum have? Or sorry, how many does boron have? 3. How many does carbon have? 4. How many does nitrogen have? 5. How many does oxygen have? 6. 7, 8, right? Then we move to the next energy level because we're filled up now, right? How many does sodium have? 1. How many does magnesium have? 2, 3, 4, 5, 6, 7, 8. You're just counting. You're just counting how many elements is it into its period. So how many, let's just pick one. How many does aluminum have? It's got 1, 2, 3. 3 valence electrons. Are we good? That's the shortcut. So it's got, sodium has 1 valence electron. The number, the Lewis symbol, what would we draw for the Lewis symbol?
The circle, and then you put like.
We wouldn't put any, yeah, okay. We would put a dot.
Yeah.
Yeah. We put a dot. And then the symbol sodium, right? Because all we're trying to show is how many valence electrons and where are they. Then the number of lone pairs. How many lone pairs does sodium have? 0. Yes, I agree. It's got paired electrons in lower energy levels, but we don't care about lower energy levels. We care only about the valence electrons. So it's got no lone pairs. It's got 0 lone pairs. How many bonding electrons does it have? 1. So how many bonds can it form? What is its bonding capacity? 1. It can form 1. Is that fairly straightforward? That's what I would like you to do right now. Go ahead and practice that. Try it out. And whip a pencil or an eraser at me or something like that if you have questions. Yeah. Okay. Hydrogen is 1. Because it has 1. So it has 1 valence. Helium has 2 electrons, and they're both in the first energy. But we're full. So when we go to the next energy, it's got 3 electrons in the first 2. Beryllium has 1, 2, 3. Boron has 1, 2, 3. Carbon has 1, 2, 3.
No. I don't use an app. You remember? I don't even know. The same number as bonding electrons.
I also mean that you can't see lights. I mean, it's kind of. I didn't like.
You could
Well, like,
figure
I
out the
thought
long
you
way
followed
that
that.
could make the board.
No, like I follow. I don't know. Yeah, I like to be able to see. If they're growing, I don't know. Yeah. It's so
Yeah, I don't know how to.
How would you put
4, 5, 6, and there's number of pairs, 2 separate bonding electrons, 2 bonding centers, and none of them are 4.
Okay, so the way I would do this.
Well, when I said bond captivity, I thought it meant like how many bonds
Wow,
would
actually.
this have?
Don't you sleep the whole day?
Yeah, something like that. I'm actually unconscious right now.
You just dreaming. No, you're dreaming.
What if I told you the truth when
So now you can tell me how many
this is
No, you're dreaming. You're dreaming. You make up. Yes, you go to school too.
yeah, something like that.
Because, wait,
That's what I'm feeling now.
No, it means how many
you know, and you gotta see
What?
Yes. Does that make sense?
Yeah.
Yeah. So fluorine can make one bond, helium can make 2 bonds.
Yeah, that was the only one that I was.
Yep. Yep. I'm happy
I
that.
have no other answer.
Bonding capacity means how many bonds can this thing form. So for example, because sodium has 1 bonding electron, it can form 1 bond. What if something had, I'm going to put an X here, and what if something had this arrangement? It could form 3 bonds, right? Yeah.
2, 3, 4, 5, 6, 7, 8.
But it's like intentional.
Here. So how many outside electrons?
5, 6, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Let's continue practicing them.
96, 97, 98, 99, 100, 101, 102, 100, 104, 105, 106. Dang it. You should wake up.
Where, no, that's not really.
I'll use my
So,
math on it. How about I'll change your pencil for your calculator? Pencil's worth more.
I know.
Use your pencil more than your calculator, right? Your pencil is worth more.
The bonding capacity, how many maximum? You know this?
How many spaces are
I don't have much. You have, don't you have your active? Okay.
Oh my god.
Oh, you broke your bomb. Then how are you going to give it back to Zoe? So I mean Zoe. No, Zoe is a religious character.
That's what you're thinking about. You're thinking about esports and I heard you.
They have similar names. Huh?
I explained to
Yeah,
You know what? If I jump over, she's going to the same thing. Zoe and Zoe the same thing. What? Matt? Then you go by what now? Alexander. Why did he change Matt? Did she get him a name change? How about you legally change your name to Steve Jobs then? Steve Jobs.
Steve Jobs.
If we were to put
And take over Apple.
how do we do it?
Yeah, you're right. Sounds like a good plan.
You're right.
$1 billion like that. God, why didn't other people just do that?
They're not smart enough.
That's 6, right? How many pairs?
Give me half of the company.
You get like
How many bonds?
You know what? I'll take my
Single electrons.
You lock them up.
So that means we can form 2 bonds here.
Dude, why do I have to be dead? Why do you get to do that?
Iman plus.
My full name is
Iman plus? What? Iman plus? Is this hinting to you being an emo?
No.
What? Are you that defensive? Are you an emo? Why? Why are you being so defensive?
We're gonna talk about it later.
How are you gonna hit me with that happy face or something?
Then we'll talk about it.
Make that a second.
Okay.
Are you taking your medicine?
So, I'm having a really hard time drawing on here because I'm not very tech savvy and there's like something off here. It's not letting me draw on the things that I would love to draw on. So I need your utmost attention because you're just going to be kind of marking this yourself, kind of a little bit, okay? When we look at sulfur, I'm not going to do the electronegativity or valence electrons. Shh. When we look at sulfur, how many lone pairs does the sulfur have? 2. It has one at the top and one at the right, correct?
Yeah.
If you were to do it the clockwise manner. How many single electrons by themselves are available to bond? 2. So we can make 2 bonds. Sulfur can make 2 bonds, right? Okay, all right. Fluorine, how many bonding electrons does it have?
3.
How many bonding electrons does fluorine have?
1.
1. It's got 3 lone pairs, but 1 bonding electron, right? So how many bonds can fluorine make? 1. Good. How many bonds can beryllium make? What's its bonding capacity? 2. What's carbon's bonding capacity? 4. Yeah, you're just, yeah, okay. That's fine. You have it on your sheet correctly. And then what's hydrogen's bonding capacity? 1. Are we okay with that? That's all we need to move on to the next step. Bonding capacity and the Lewis diagram is all we need to move on to the next step, okay? Now the backside, you can't do yet. I just wanted you to practice that for now. The backside we are going to work on tomorrow. But before we do that, we got to learn what the hell a Lewis structure for a molecule is. So let's do it. Perfect. 3.2 Lewis structures. What time is it? It is 1:34. We have 20 minutes left in class.
How do you have glasses?
Why aren't you wearing them?
I should get glasses.
Me too.
Dude, my eyes have gotten worse to the point where
Stop using glasses. That's what I'm wearing glasses. I try not to wear glasses because your eyes get used to your glasses, and when you take away glasses, you're kind of.
yeah, that works, Joe.
I don't know, but something like that. No, it's because the glasses are making you age, so your eyesight is getting worse.
One of the most resigned no's I've ever done. Catch Cassidy. No.
If your glasses make you age, then your eyes change.
Well, it's a good thing my glasses don't make me age. That's not possible.
Okay. So, we're now on to 3.2 Lewis structures of molecules. So we're kind of okay with Lewis structures of atoms, or at least hopefully we are. Draw the Lewis structure of a fluorine atom. How many valence electrons does fluorine have?
1, 2, 3, 4, 5, 6, 7.
It's got 7. Don't think too much. It'll make you cough. Okay? So 1, 2, 3, 4, 5, 6, 7. Good. That's the Lewis structure of a fluorine atom. How many lone pairs does it have?
3.
1, 2, 3. There are 3 pairs of electrons here. The reason why we call them lone pairs is because those don't form bonds with other things, and at least they don't yet. Okay? How many bonding electrons does fluorine have? 1. It's got 1 single bonding electron, right? That's the only electron available for bonding. How many fluorines would be needed to combine in order to complete their octets? What I want you to think of is if we had a fluorine, how many other fluorines would I need in order to complete all of their octets?
1 more.
Just 1 more. Does that make sense?
1 more.
So if I had another one here, I'm going to move it over, and let's say I made this one, and I said, okay, 1, 2, 3, 4, 5, 6, 7. Is there enough electrons to go around for everybody to complete their octet? Yeah. So what's happening is this fluorine is kind of sharing, it's sharing the electron from that fluorine, and this fluorine is sharing the electron of that fluorine, and we've made a bond. How many bonds have we made? 1 bond. And so we could draw this, we could redraw this as a structure. The structure would look like this. Eurostructure. So it's a fluorine bonded with another fluorine. Now, hopefully you'll notice we're kind of ignoring the lone pairs for now, okay? And that's because right now, as far as you're concerned, they don't really do anything. This is what we call a polyatomic element. Fluorine is a polyatomic element because it's actually more stable if there's 2 fluorine atoms combined together. That way, they're both happy because they have their octets. The completion of the octet is a way to explain why some elements have more than 1 atom in their molecules. Example number 2, draw the Lewis structure of oxygen. Go ahead and do that for me, please. I know you've already done it, probably a couple times, but just do it again. Yeah, Luke, stop bugging Jared. Don't apologize to me, apologize to Jared. What's the symbol for oxygen? Oh. Alright. And how many valence electrons does it have? 6. 1, 2, 3, 4, 5, 6. Perfect. Now, how many bonds can oxygen form? 2. We can form 2, right? How many bonds could we form using an oxygen? We can form 2. Alright, perfect, no problem. To show a structural formula, draw a line for each pair of bonding electrons and omit any lone pairs. What we're going to do, what I want to ask you, how many oxygen atoms are required in order to complete their octets?
2.
You just need 2. Why do you only need 2? If this oxygen shared both of their electrons with another oxygen, so think of me with 4 arms, right? Basically is what we're, don't think of me, whatever. So let's try and draw this. If this oxygen, I'm going to draw this in kind of a weird way, so just don't draw it yet, okay? Don't draw it yet, please. I'm going to draw this in a weird way. 1, 2, 3, 4, 5, 6. And then I'm going to group them together. And I'm going to clone them. Perfect. Awesome. So if I took this, and if I just kind of rotated a little bit, and then I took this, and I kind of rotated it a little bit, is there any way that we could get these oxygens to share both of their electrons at the same time?
Yes.
Does that kind of make sense? Kind of. So how many bonds? Now these are in a bond and these are in a bond. They're being shared between these 2 oxygen atoms. So how many bonds are in between these oxygen atoms? 2. So we would draw this. Oxygen, oxygen. This is what we call a double bond. There are 2 bonds holding these atoms together. Quinn.
Yeah, if sulfur has the same amount of valence electrons as oxygen, why is it S8 so that's 2?
And then the reason why that is because instead of oxygen is this big, okay? Now is sulfur, what energy level are the valence electrons in for oxygen? What row does it occupy? The 2nd energy level, right? What about sulfur? The 3rd energy level. So which one's bigger? Sulfur. So what that means is that instead of drawing oxygen like this, I should draw sulfur like this. Do you know what I mean? Like if I was to show their actual size. So sulfur is bigger. So what that means is that sulfur group clone. Wim, you're asking me a really complicated question, so I just need you to understand that you're never going to be tested on this, right? This is just because you asked and because I want to answer your question. So this sulfur and this sulfur, they could still share their electrons, but it's a lot harder to share their electrons. Do you see how they're starting to bump up against each other a little bit? It's way easier for this sulfur. Instead of doing that, it's just like, you know what? Screw you. I'm going to make one with this person, and then I'm going to make another bond with another sulfur down here, and then another one over here. Yeah, because of sulfur's size, it would rather form bonds I kind of screwed it up, but hopefully you understand what I'm talking about. It's supposed to look like a giant octagon. And that's because sulfur's too big for it to be able to share both of its electrons. Now, you're never going to get tested on that. If that confused the hell out of you, then just wipe it from your memory, okay? Just don't worry about it. But because you asked, I'm answering. Okay, use bonding theory to draw the Lewis structures. No, I don't want you to. I want you to do 3. Try number 3. Yep. Yep.
know it, right?
So hold on a second.
I'm like, are you kidding me? God, it's funny.
Do the questions or
It's a triple bond.
It's really bad, but that's my God.
Every time I check it, it's like
If I'm right.
yeah, every.
I don't know.
Imagine being a rat in a skip. Living in the sewers. Oh, MC Tom. Come on, you gotta share your rap verse. You gotta share your rap verse. My name is Lil. It's Kim. Sounds like a Grinch. Wait, is this your skipping?
Okay, this is kind of difficult for me to do. Okay, so just chill out for a second. How many bonding electrons does nitrogen have?
2, 3, 4.
What does the Lewis diagram for nitrogen look like?
3.
2 on top and then 1 on the other side.
Right? Now, it's hard to see this because this is a two-dimensional picture that's representing 3 dimensions. So when you see the one on the right, left, and bottom sides, okay, it's really like this, the right, left, and bottom sides. And then there's something on top, right? There's a lone pair up here, okay? Is it possible for these nitrogens to share all 3 of their bonding electrons at the same time? Is that possible? Yes, it's totally possible. This was really hard for me to do, by the way. Okay, so now, the way we draw this in 3 dimensions, and we'll go over how to do this later, is we would go N, and it's got its 1, 2, 3 bonding electrons, and on the other side there's an N with its lone pair, and it's 1, 2, 3 bonding electrons. So what's being made here? That's a triple bond. Is that kind of okay? It's hard. Would you agree it's hard to represent a 3-dimensional object in 2 dimensions? Yes, so we have to kind of bend the rules a little bit. We have to say this is what's actually going on. Okay? Now, tomorrow we're going to go through a bunch of information, right? We're going to recap bonding capacity. We're going to recap bonding capacity, and then we're going to jump into how to determine the Lewis formula for an entire molecule. It involves a set of rules, and you just have to accept that this is the reason why, or this is the way that we do it. So the set of rules, if you want to read it over tonight, you're more than welcome to. We're going to start talking about it tomorrow at the beginning of class. Now, the quiz that you have on Friday, is all about Lewis structures of molecules. Okay? There's a little bit of atoms. If you're not going to be here tomorrow, but you are going to be here on Friday,
You're gonna fail.
well, you're not going to know the information for the quiz, right? So that's going to be pretty tough. So just make sure that you're actually here. Make sure you're actually here on time.